Okay, so what we have here is part 2 of processing the kinetic data. So what I've done is I've made a spreadsheet here that contains nothing but what you should have when you finish the experiment, which is a whole set of times and some volumes of 2 of the reagents that are critical. If you watched part 1 of this video, you know that since all of the reactions have a constant volume, that doing the calculations for the concentration at the start of the reaction is relatively simple, but being that Excel is good for very little else, we like to let it do iterative formulas for us. Since we have a whole crate of concentrations to deal with, it's better to let Excel handle it if we can. So the way we do that is we put a formula in place. So I have in the column C here, I have the S208 volume at the standard concentration. Column D, I have the volume of the iodide ion solution of the original concentrated solutions from the stock bottles. So the way that we do this is that we use the equal sign to tell Excel we're using a formula. We use cell numbers like this, C2, to refer to which column first and then which row we're dealing with. And then, since we know that that is 0.2 molar, and we know that the total final volume is 19 milliliters, which will cancel out the milliliter volume here, we have a calculation of the concentration. If you're a little unsure on how that came about, go back and look at the first video for the lab series because it covers this in a lot of detail. The reason I wanted to do that is because Excel allows you to drag a formula. So if you notice on the bottom right corner, there's a little black dot here, a little black square. If I run the cursor over that, you can see the cursor changes. If I drag from there all the way down, it will increment the formula based on the cells. So what it does is, the original one I typed in, see it has C2 here. If I move down, it's moved to C3. So now I'm in the next trial, the next trial, the next trial, all the way down. The ones where nothing happens, I spaced this out to make it a little more obvious since that's the way the data sheet was laid out. So you just go back and get rid of those so that they're not there later for other calculations we're going to do. Same thing here. I can actually even increment the formula sideways if I want. I can just drag it to the side and it will increment from column C to column D, which is what I want to do. So I can take that now, drag it all the way down, same problem as before, same final volume, same initial concentration. So all I'm changing in each case are those numbers. Are the volumes of each one. So in the first 4, the volume of the iodide ion doesn't change from the stock solution, so its concentration doesn't change in the final answer. The last piece, the concentration relationship between the initial rate and the time is just an inverted thing, but we had a standard concentration change. So we had a decrease in the concentration of the S203 ion as we went through this. It was 6.32 times 10 to the minus 4. So my rate is that change divided by the time. You'll notice I put all the times here in seconds all the way up and down so that there's no ambiguity. Make sure you do that. Don't put this in, as minutes in part of it and time in seconds in the other. That will make a mess of your units and a mess of all your calculations. So what I'm going to do is put that in, and the way that Microsoft deals with a 10 to the minus is to use the capital letter E. And I'm going to divide that. I'm going to put it in parentheses just to be safe. Probably not necessary, but just in case. And I'm going to divide that by the time, which in this is column B, and for this trial is B2. So I'm going to divide that by B2, and that's going to give me my rate, which I can pull that all the way down as well. And again, go back and get rid of the ones that we didn't use because I just left spaces to make this a little neater and a little more obvious which data sheet we're dealing with. Okay, so if you've done the calculations from the lab, you did them following video number 1, then you should already have this data. It should not be a surprise to you. So you should be able to check this and say, oh yeah, that's the number I got. So I'm using sample data. Yours will vary slightly. This is from 2014 where I got this data, but it doesn't change that much year to year because, hey, it is the same reaction. Okay, so now we need to actually compare these rates to let us solve for X and Y, the reaction order for S208 ion and the reaction order for the iodide ion. The way we do that is we set up a ratio between these rates. just as we showed in the first video, only we don't have to do it for every one, we can just drag it downwards. So in this case, what I want is rate for trial 1 divided by rate for trial 2, so that's going to be G2 and G3. And if I want, I can even drag that downward. Now this is the case where you've got to be a little careful with those zeros because you're going to have a division by zero error because there's no trial there, so you've got to get rid of those. There are only 3 ratios for each one, not 4. Okay, so how do we get from that to X? Well, if you watched the first video, the mathematics of this concentration for the S208 in the first 4 trials simplifies down to the rate ratio, what I have just solved for in column H, is equal to 2 to the X. So what I can do is I can kind of see that 2 to the X equals 2.02 is pretty sure X is 1, but just in case I had some doubts, let's do it the right way. So again, equal sign for a formula. What I'm going to say is that is the natural log of H2 and I'm going to divide that by the natural log of 2 all the way down. And that should give me X. So in this case now I have 1.01, or 1.02 if I round it off, 1.0, 1.07. We can safely say X is 1. We can do exactly the same thing for Y. You could use the same column and just drag the formula, but I wanted to make this clear so that it wouldn't be a question. So same formula. This time we're in cell number 7. You'll highlight so you can always check to make sure you have the right one. And we're going to take that and divide it by the natural log of 2 because our second one was a natural log of 2 as well. It was 2 to the Y is the ratio between rates for the second set of trials. So we have here, you can see the data is not quite as good. We're kind of all over the place, 0.88, 1.19. But if we average that, we're still going to end up pretty close to 1, which is what it should be. So then we can go back to any of these, and that includes even the ones where I didn't do anything with them yet because their ratios are less relevant, and solve for K by saying that K is going to be equal to the rate, which is, and I can select it by just clicking on it, so it puts up the G2, divided by, and since these are both first order, X and Y are both 1, then I can just divide by that times that. And that gives me the equation, which will let me solve for K, and that I can drag for every trial all the way down the table, because that's relevant for every one of these. Again, we have to get rid of the ones where there's no data, because I left spaces, just to make it a little easier to see. Okay, now what we would do ideally is we would say at 1 temperature, this is, all of the first 8 trials are the same temperature, so these Ks should all be pretty close. And you can see 0.469, 463, 466, I said 0.00466. That one's a little bit weird, but they're reasonably close to each other, but not great, because like I said, the second trial, the data are not as consistent. Otherwise, we'd be looking at 2.0 here, 1.99 here, and we're not. So we have to be kind of aware of that, but the point of doing a lot of data points is you can average the middle, average out the error. I would tend to be a little more leery of the second set just because the Y value doesn't work out as quite to be an integer. Okay, so at that point we have a rate constant at 1 temperature, but it's kind of questionable. The next set, trials 9 through 12, were the temperature trials, which probably were one of the most unpleasant things you've ever done in a lab setting if you tried to do those, because you have to keep the vials and keep the flasks in hot or cold water and wait till they equilibrate and then mix them and get them back in there very quickly. It's kind of a sloppy thing to do, but it's the only way to get data for the energy of activation, which requires us to use multiple K values because that's related by the Arrhenius equation to the temperature. So I have the temperatures for those trials already down here in Kelvin. Make sure that your units here are correct. So what we're going to need though is an inverse relationship there for the temperatures. So what I'm going to do is invert that, and then I can just drag that down to the cells I'm curious about, which are trials 9 through 12. And I'm also going to need the natural log of K. So again, relatively simple, equals for every formula, and then we're good. So we take that and drag that down, and now I have my data for 1 over t versus natural log of K. So now I want to graph this. What I did is this. I would just select the ones I'm curious about, the ones I actually have data for, and then go to insert, scatter, XY scatter with no points. And Microsoft does the ever-intelligent thing of making it as useless as possible when you do this. So first and foremost, put it on a separate sheet where you can actually see it. That used to be the default. For some reason, they've changed their mind. Apparently, being able to see the graph is not desirable in Microsoft world. So a few things that I recommend for people when they do graphs, and this is how I teach my class to do them. You don't need a legend if you're not doing multiple series, and we generally don't, so get rid of it. There are layouts here that are close to what I'd like to see, which is it has to have grid lines, look like graph paper, with some axis labels, that sort of thing. So you can actually take one of the default layouts, or you can do it by hand. I don't know if these are default layouts for everyone or whether they're custom to mine, so I'm going to do it the hard way just so you see how to do it. First, grid lines. Under layout for chart tools, turn them all on, major and minor. All right, we want this to look as much like graph paper as possible because we're actually caring about what it looks like, and we want to be able to interpret the data. We just have a couple of things to do. We need some axis titles to go with it. So on the horizontal axis, I tend to put it below the axis, and then you can type into the formula bar what you want it to be. In this case, the x-axis is the inverted temperature, so we can put 1 over T there. We would write K minus 1 or 1 over Kelvin as units, but Microsoft doesn't allow us to do exponents in their formulas, at least as subscripts, so we have to kind of make it look a little sloppy. Same thing for the vertical axis. I tend to use rotated. It looks a little bit better to me. This is our natural log of the K value. Then we need a chart title to tell us what this is. So I tend to use the above the chart. It moves down the graph paper look, and just give it something that is useful and descriptive so that we know what it actually refers to. Try to spell it correctly if you can. Okay. Now the last thing we need is an actual trend line. That's over here. Place for a lot of mistakes to happen if you're not careful. First, you generally don't want to select a linear trend line. I know that sounds dumb because it looks like it's linear, but the reason for that is the linear trend line does not give us a couple of options we really need to see. So we tend to do it as, I tend to do it as using more options. Linear is the default anyway, but we need a couple of things here. We need to see the equation. We need to see the r-squared value, which tells us whether our equation is actually fitting the data very well or not. And in a lot of cases in chemistry, not this one, but a lot of them, like absorbance, like density, will need to force the y-intercept. This case, we don't want to do that. We don't need to do that. It would make a very messy trend line if we did. So we do that. It gives us our trend line. We can move this up. I tend to drag it up here where you can see it up off of the graph paper background. And this, the slope of the line, is actually the negative energy of activation over R. So from this, you can actually work out the energy of activation relatively directly. It should be in the neighborhood of between 50 and 60 kilojoules per mole. Keep in mind that the R value that you get, 8.31 joules per mole Kelvin, is not in kilojoules. Joules per mole Kelvin is what I said. Make sure you get the units straight. Otherwise, you're going to have a problem. You're going to get a ridiculously large or small number. Keep track of that. So make sure if you're going to use that R value, which you have to use, convert it to kilojoules first. So you'll have 8.31 times 10 to the minus 3 kilojoules per mole Kelvin. Then you'll get a reasonable energy of activation number, which would be somewhere probably between 50 and 60. Depending on your instructor, they may spend a lot of time with these last ones. The last 4 were catalytic trials to show you that for a reaction where a catalyst exists, it speeds up. Well, that's not usually such an easy thing to do as a linear a linear relationship because, first of all, you're using a drop or two drops, not an exact volume of a catalyst. It does slightly change the concentrations of everything else because the catalyst solution does have a volume, even if it is a relatively small one. But what you want to see is do that against the version that doesn't have a catalyst. So notice here, these are the ones where the S2O8 concentration was unchanged. So these are trial 17 is basically the catalytic version of trial 5, and so on all the way down. So you can look at those and say, all right, it's a rate constant here of 5.5 times 10 to the minus 3 versus 7.4. It's roughly 1.5 times as fast. But you can see that's not going to be really consistent. If you really wanted to see it, what you would do is say, all right, so give me this and the rate constant, which is directly proportional to the rate. You could use the rate column if you want. You're going to get exactly the same answer. And divide that by the uncatalyzed version here. Well, actually, let's not do that. Let's put it over here out of the way. We don't want it in the wrong column if you print out the spreadsheet. So what I want to see is just ratio-wise what happens, comparing it to the uncatalyzed. And this is what it looks like. So if I'm looking at this, depending on, this probably did not have the same amount of catalyst added in both cases, because you can see it's not really consistent, but it is a good bit faster. Just to make a point, let's show that you can actually do this with the rates themselves and get the same numbers. I don't like to leave questions unanswered. So you can do this and you will get exactly the same answers. So if I did the ratio with the rate constants, which are the column K here, coincidentally column K and the rate constant K, not intentional. I wish I was that good that I could do that intentionally. Or I can use the rates themselves from column G. I get the same numbers because they are directly proportional once the concentrations are left identical. So what we're seeing here is anywhere from 1.3 to about 2.1 times as fast. So this is a catalyst that does speed things up. The way it does it, of course, if you talked about this in lecture, is it chops the top off of the energy of activation so that it lowers that. You could even, if you wanted to, compare temperature trials in the catalytic version to these and actually work out what the new energy of activation is. We don't go that far because the temperature trials are relatively difficult with our equipment anyway, but you could do that, and what you'd see is it drops it down a good bit because otherwise you wouldn't see a real acceleration. All right, so with this you now have, for columns E, F, and G, along with H, I, and J here, you have backup to things that you should have already done calculation-wise, same for K actually, but at least you can figure out a way to do it a lot more quickly, because if you had to do these one by one, which you probably did, it takes quite a long time, and that's one of the few things that spreadsheet programs like Excel are really good for, is getting past the redundant. It can actually, you type in a formula once, drag it down, and it's done. It does it over and over and over automatically without you having to keep punching the calculator buttons. So it's a good tool for that. It's also a good tool for graphical representations, although Microsoft has some very odd ideas of what your default should be, but with a little bit of repair you can actually make it look like a proper and professional graph of the type you would actually see in the literature for somebody reporting new data in the sciences. So hopefully this helps, and if you have questions just email me and I'll answer them relatively quickly. And